Hi students, in this chapter nuclei we are going to study about the atomic masses and composition of nucleus. We are also going to study about the discovery of neutrons, the size of the nucleus and mass energy, and also about the nuclear binding energy and nuclear force, and also about radioactivity, nuclear energy, nuclear fission and fusion reactions, and also about the controlled thermonuclear fusion.
Nuclei. Introduction. In the previous chapter, we have learned that in every atom, the positive charge and mass are densely concentrated at the center of the atom forming its nucleus. The overall dimensions of a nucleus are much smaller than those of an atom. Experiments on scattering of alpha particles demonstrated that the radius of a nucleus was smaller than the radius of an atom by a factor of about 10 power 4. This means the volume of a nucleus is about 10 power minus 12 times the volume of the atom. In other words, an atom is almost empty. If an atom is enlarged to the size of a classroom, the nucleus would be of the size of pinhead. Nevertheless, the nucleus contains more than 99.9% of the mass of an atom. Does the nucleus have a structure, just as the atom does? If so, what are the constituents of the nucleus? How are these held together? In this chapter, we shall look for answers to such questions. We shall discuss various properties of nuclei such as their size, mass and stability, and also associated nuclear phenomena such as radioactivity, fission and fusion. Atomic masses and composition of nucleus. The mass of an atom is very small, compared to a kilogram. For example, the mass of a carbon atom, 12C, is 1.992647 times 10 power minus 26 kilograms. Kilogram is not a very convenient unit to measure such small quantities. Therefore a different mass unit is used for expressing atomic masses. This unit is the atomic mass unit, U, defined as 1/12 of the mass of the carbon, 12C, atom. According to this definition, 1 U equals 1.660539 x 10 power minus 27 kilograms. The atomic masses of various elements expressed in atomic mass unit, U, are close to being integral multiples of the mass of a hydrogen atom. There are, however, many striking exceptions to this rule. For example, the atomic mass of chlorine atom is 35.46 U. Accurate measurement of atomic masses is carried out with a mass spectrometer. The measurement of atomic masses reveals the existence of different types of atoms of the same element, which exhibit the same chemical properties, but differ in mass. Such atomic species of the same element differing in mass are called isotopes. In Greek, isotope means the same place, i.e. they occur in the same place in the periodic table of elements. It was found that practically every element consists of a mixture of several isotopes. The relative abundance of different isotopes differs from element to element. Chlorine, for example, has two isotopes having masses 34.98 U and 36.98 U, which are nearly integral multiples of the mass of a hydrogen atom. The relative abundances of these isotopes are 75.4 and 24.6%, respectively. Thus, the average mass of a chlorine atom is obtained by the weighted average of the masses of the two isotopes, which works out to be 35.47 U. Which agrees with the atomic mass of chlorine. Even the lightest element, hydrogen, has three isotopes having masses 1.0078 U, 2.0141 U, and 3.0160 U. The nucleus of the lightest atom of hydrogen, which has a relative abundance of 99.985%, is called the proton. The mass of a proton is MP equals 1.00727 U equals 1.67262 by 10 power minus 27 kilograms. This is equal to the mass of the hydrogen atom equals 1.00783 U minus the mass of a single electron, Me equals 0.00055 U. The other two isotopes of hydrogen are called deuterium and tritium. Tritium nuclei, being unstable, do not occur naturally and are produced artificially in laboratories. The positive charge in the nucleus is that of the protons. A proton carries 1 unit of fundamental charge and is stable. It was earlier thought that the nucleus may contain electrons, but this was ruled out later using arguments based on quantum theory. All the electrons of an atom are outside the nucleus. We know that the number of these electrons outside the nucleus of the atom is Z, the atomic number. The total charge of the atomic electrons is thus minus Ze, and since the atom is neutral, the charge of the nucleus is plus Ze. The number of protons in the nucleus of the atom is, therefore, exactly Z, the atomic number. Discovery of neutron. Since the nuclei of deuterium and tritium are isotopes of hydrogen, they must contain only one proton each. But the masses of the nuclei of hydrogen, deuterium and tritium are in the ratio of 1:2 to 3. Therefore, the nuclei of deuterium and tritium must contain, in addition to a proton, some neutral matter. The amount of neutral matter present in the nuclei of these isotopes, expressed in units of mass of a proton, is approximately equal to 1 and 2, respectively. This fact indicates that the nuclei of atoms contain, in addition to protons, neutral matter in multiples of a basic unit. This hypothesis was verified in 1932 by James Chadwick, who observed emission of neutral radiation when beryllium nuclei were bombarded with alpha particles. It was found that this neutral radiation could knock out protons from light nuclei such as those of helium, carbon and nitrogen. The only neutral radiation known at that time was photons, electromagnetic radiation. Application of the principles of conservation of energy and momentum showed that if the neutral radiation consisted of photons, the energy of photons would have to be much higher than is available from the bombardment of beryllium nuclei with alpha particles. The clue to this puzzle, which Chadwick satisfactorily solved, was to assume that the neutral radiation consists of a new type of neutral particles called neutrons. From conservation of energy and momentum, he was able to determine the mass of new particle, as very nearly the same as mass of proton. The mass of a neutron is now known to a high degree of accuracy. It is Mn equals 1.00866 U equals 1.6749 times 10 power minus 27 kilograms. Chadwick was awarded the 1935 Nobel Prize in Physics for his discovery of the neutron. A free neutron, unlike a free proton, is unstable. It decays into a proton, an electron and an antineutrino, another elementary particle, and has a mean life of about 1000 seconds. It is, however, stable inside the nucleus. The composition of a nucleus can now be described using the following terms and symbols. Z, atomic number equals number of protons. N, neutron number equals number of neutrons. A, mass number equals Z plus N equals total number of protons and neutrons. One also uses the term nucleon for a proton or a neutron. Thus the number of nucleons in an atom is its mass number. A nuclear species or nuclides are shown by the notation AX, where X is the chemical symbol of the species. For example, the nucleus of gold is by 79O197. It contains 197 nucleons, of which 79 are protons and the rest 118 are neutrons. The composition of isotopes of an element can now be readily explained. The nuclei of isotopes of a given element contain the same number of protons, but differ from each other in their number of neutrons. Deuterium, 2H, which is an isotope of hydrogen, contains 1 proton and 1 neutron. Its other isotope tritium, 3H, contains 1 proton and 2 neutrons. The element gold has 32 isotopes, ranging from A equals 173 to A equals 204. We have already mentioned that chemical properties of elements depend on their electronic structure. As the atoms of isotopes have identical electronic structure, they have identical chemical behavior and are placed in the same location in the periodic table. All nuclides with same mass number A are called isobars. For example, the nuclides 3H and 3 helium are isobars. Nuclides with neutron number N but different atomic number Z, for example 198 Hg and 197 O, are called isotones. Size of the nucleus. As we have seen in Chapter 12, Rutherford was the pioneer who postulated and established the existence of the atomic nucleus. At Rutherford's suggestion, Geiger and Marsden performed their classic experiment on the scattering of alpha particles from thin gold foils. Their experiments revealed that the distance of closest approach to a gold nucleus of an alpha particle of kinetic energy 5.5 million electron volts is about 4.0 times 10 power minus 14 meters. The scattering of alpha particle by the gold sheet could be understood by Rutherford by assuming that the Coulomb repulsive force was solely responsible for scattering. Since the positive charge is confined to the nucleus, the actual size of the nucleus has to be less than 4.0 times 10 power minus 14 meters, If we use alpha particles of higher energies than 5.5 million electron volt, the distance of closest approach to the gold nucleus will be smaller, and at some point the scattering will begin to be affected by the short-range nuclear forces, and differ from Rutherford's calculations. Rutherford's calculations are based on pure Coulomb repulsion between the positive charges of the alpha particle and the gold nucleus. From the distance at which deviations set in, nuclear sizes can be inferred. By performing scattering experiments in which fast electrons, instead of alpha particles, are projectiles that bombard targets made up of various elements, the sizes of nuclei of various elements have been accurately measured. It has been found that a nucleus of mass number A has a radius given by the equation 13.5, where r equals 1.2 times 10 power minus 15 meters, equals 1.2 fm, 1 fm equals 10 power minus 15 meters. This means the volume of the nucleus, which is proportional to r cube, is proportional to A, thus the density of nucleus is a constant, independent of A, for all nuclei. Different nuclei are like a drop of liquid of constant density. The density of nuclear matter is approximately 2.3 times 10 power 17 kilograms m power minus 3. This density is very large compared to ordinary matter, say water, which is 10 power 3 kilograms m power minus 3. This is understandable, as we have already seen that most of the atom is empty. Ordinary matter consisting of atoms has a large amount of empty space. Mass energy and nuclear binding energy. Mass, energy. Einstein showed from his theory of special relativity that it is necessary to treat mass as another form of energy. Before the advent of this theory of special relativity, it was presumed that mass and energy were conserved separately in a reaction. However, Einstein showed that mass is another form of energy, and one can convert mass energy into other forms of energy, say kinetic energy and vice versa. Einstein gave the famous mass-energy equivalence relation. E equals mc square. Here the energy equivalent of mass m is related by the above equation, and c is the velocity of light in vacuum and is approximately equal to 3 times 10 power 8 meters s power minus 1. Experimental verification of the Einstein's mass-energy relation has been achieved in the study of nuclear reactions amongst nucleons, nuclei, electrons and other more recently discovered particles. In a reaction, the conservation law of energy states that the initial energy and the final energy are equal provided the energy associated with mass is also included. This concept is important in understanding nuclear masses and the interaction of nuclei with one another. They form the subject matter of the next few sections. Nuclear binding energy. In section 13.2 we have seen that the nucleus is made up of neutrons and protons. Therefore it may be expected that the mass of the nucleus is equal to the total mass of its individual protons and neutrons. However, the nuclear mass m is found to be always less than this. For example, let us consider oxygen nucleus, a nucleus which has 8 neutrons and 8 protons. We have mass of 8 neutrons equals 8 times 1.00866 U. Mass of 8 protons equals 8 times 1.00727 U. Mass of 8 electrons equals 8 times 0.00055 U. Therefore the expected mass of 16O nucleus equals 8 times 2.01593 U equals 16.12744 U. The atomic mass of O16 found from mass spectroscopy experiments is seen to be 15.99493 U. Subtracting the mass of 8 electrons, 8 times 0.00055 U, from this, we get the experimental mass of O16 nucleus to be 15.99053 U. Thus, we find that the mass of the O16 nucleus is less than the total mass of its constituents by 0.13691 U. The difference in mass of a nucleus and its constituents, delta M, is called the mass defect, and is given by the equation 13.7. What is the meaning of the mass defect? It is here that Einstein's equivalence of mass and energy plays a role. Since the mass of the oxygen nucleus is less than the sum of the masses of its constituents, 8 protons and 8 neutrons, in the unbound state, the equivalent energy of the oxygen nucleus is less than that of the sum of the equivalent energies of its constituents. If one wants to break the oxygen nucleus into 8 protons and 8 neutrons, this extra energy delta mc square has to be supplied. This energy required EB is related to the mass defect by EB equal to delta mc square. If a certain number of neutrons and protons are brought together to form a nucleus of a certain charge and mass, an energy EB will be released in the process. The energy E flat is called the binding energy of the nucleus. If we separate a nucleus into its nucleons, we would have to supply a total energy equal to EB to those particles. Although we cannot tear apart a nucleus in this way, the nuclear binding energy is still a convenient measure of how well a nucleus is held together. A more useful measure of the binding between the constituents of the nucleus is the binding energy per nucleon, EBN, which is the ratio of the binding energy E flat of a nucleus to the number of the nucleons, A, in that nucleus. EBN equals E flat, A. We can think of binding energy per nucleon as the average energy per nucleon needed to separate a nucleus into its individual nucleons. Figure 13.1 is a plot of the binding energy per nucleon EBN versus the mass number A for a large number of nuclei. We notice the following main features of the plot. 1. The binding energy per nucleon, EBN, is practically constant, that is, practically independent of the atomic number for nuclei of middle mass number, 30 less than A less than 170. The curve has a maximum of about 8.75 million electron volt for A equals 56 and has a value of 7.6 million electron volt for A equals 238. 2. EBN is lower for both light nuclei, a less than 30, and heavy nuclei, a greater than 170. We can draw some conclusions from these two observations. The force is attractive and sufficiently strong to produce a binding energy of a few million electron volt per nucleon. The constancy of the binding energy in the range 30 less than A less than 170 is a consequence of the fact that the nuclear force is short-ranged. Consider a particular nucleon inside a sufficiently large nucleus. It will be under the influence of only some of its neighbors, which come within the range of the nuclear force. If any other nucleon is at a distance more than the range of the nuclear force from the particular nucleon, it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have a maximum of p neighbors within the range of nuclear force, its binding energy would be proportional to pages. Let the binding energy of the nucleus be pk, where k is a constant having the dimensions of energy. If we increase A by adding nucleons, they will not change the binding energy of a nucleon inside. Since most of the nucleons in a large nucleus reside inside it and not on the surface, the change in binding energy per nucleon would be small. The binding energy per nucleon is a constant and is approximately equal to pk. The property that a given nucleon influences only nucleons close to it is also referred to as saturation property of the nuclear force. A very heavy nucleus, say A equals 240, has lower binding energy per nucleon compared to that of a nucleus with A equals 120. Thus, if a nucleus A equals 240 breaks into two A equals 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the process. It has very important implications for energy production through fission, to be discussed later in section 13.7. 1. Consider two very light nuclei, a less than or equal to 10, joining to form a heavier nucleus. The binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process of fusion. This is the energy source of Sun, to be discussed later in section 13.7. 2. Nuclear force. The force that determines the motion of atomic electrons is the familiar Coulomb force. In section 13.4, we have seen that for average mass nuclei the binding energy per nucleon is approximately 8 million electron volt, which is much larger than the binding energy in atoms. Therefore, to bind a nucleus together there must be a strong attractive force of a totally different kind. It must be strong enough to overcome the repulsion between the positively charged protons and to bind both protons and neutrons into the tiny nuclear volume. We have already seen that the constancy of binding energy per nucleon can be understood in terms of its short range. Many features of the nuclear binding force are summarized below. These are obtained from a variety of experiments carried out during 1930 to 1950. 1. The nuclear force is much stronger than the Coulomb force acting between charges or the gravitational forces between masses. The nuclear binding force has to dominate over the Coulomb repulsive force between protons inside the nucleus. This happens only because the nuclear force is much stronger than the Coulomb force. The gravitation force is much weaker than even Coulomb force. 2. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. This leads to saturation of forces in a medium or a large-sized nucleus, which is the reason for the constancy of the binding energy per nucleon. A rough plot of the potential energy between two nucleons as a function of distance is shown in the figure 13.2. The potential energy is a minimum at a distance r0 of about 0.8 fm. This means that the force is attractive for distances larger than 0.8 fm and repulsive if they are separated by distances less than 0.8 fm. The nuclear force between neutron-neutron, proton-neutron and proton-proton is approximately the same. The nuclear force does not depend on the electric charge. Unlike Coulomb's law or the Newton's law of gravitation, there is no simple mathematical form of the nuclear force. Radioactivity. A. H. Becquerel discovered radioactivity in 1896 purely by accident. While studying the fluorescence and phosphorescence of compounds irradiated with visible light, Becquerel observed an interesting phenomenon. After illuminating some pieces of uranium potassium sulfate with visible light, he wrapped them in black paper and separated the package from a photographic plate by a piece of silver. When, after several hours of exposure, the photographic plate was developed, it showed blackening due to something that must have been emitted by the compound and was able to penetrate both black paper and the silver. Experiments performed subsequently showed that radioactivity was a nuclear phenomenon in which an unstable nucleus undergoes a decay. This is referred to as radioactive decay. 3 types of radioactive decay occur in nature. 1. Alpha decay, in which a helium nucleus is emitted. 2. Beta decay, in which electrons or positrons, particles with the same mass as electrons, but with a charge exactly opposite to that of electron, are emitted. 3. Gamma decay, in which high energy, hundreds of kilo-electron volt or more, photons are emitted. Nuclear energy. The curve of binding energy per nucleon EBN, given in figure 13.1, has a long flat middle region between A equals 30 and A equals 170. In this region the binding energy per nucleon is nearly constant, 8.0 million electron volt. For the lighter nuclei region, A less than 30, and for the heavier nuclei region, A greater than 170, the binding energy per nucleon is less than 8.0 million electron volt, as we have noted earlier. Now, the greater the binding energy, the less is the total mass of a bound system, such as a nucleus. Consequently, if nuclei with less total binding energy transform to nuclei with greater binding energy, there will be a net energy release. This is what happens when a heavy nucleus decays into 2 or more intermediate mass fragments, fission, or when light nuclei fuse into a heavier nucleus, fusion. Exothermic chemical reactions underlie conventional energy sources such as coal or petroleum. Here the energies involved are in the range of electron volts. On the other hand, in a nuclear reaction, the energy release is of the order of million electron volt. Thus for the same quantity of matter, nuclear sources produce 1,000,000 times more energy than a chemical source. Fission of 1 kilogram of uranium, for example, generates 10 power 14 joule of energy. Compare it with burning of 1 kilogram of coal that gives 10 power 7 joule. Fission. New possibilities emerge when we go beyond natural radioactive decays and study nuclear reactions by bombarding nuclei with other nuclear particles such as proton, neutron, alpha particle, etc. A most important neutron-induced nuclear reaction is fission. An example of fission is when a uranium isotope U-92 and 235 bombarded with a neutron breaks into two intermediate mass nuclear fragments, barium and krypton, with 3 neutrons. The same reaction can produce other pairs of intermediate mass fragments as given by the equations 13.11 and 13.12, thereby releasing 4 or 2 neutrons. The fragment products are radioactive nuclei. They emit beta particles in succession to achieve stable end products. The energy released, the Q value, in the fission reaction of nuclei like uranium is of the order of 200 million electron volt per fissioning nucleus. This is estimated as follows. Let us take a nucleus with A equals 240 breaking into 2 fragments each of A equals 120. Then, EBN for A equals 240 nucleus is about 7.6 million electron volt, EBN for the 2A equals 120 fragment nuclei is about 8.5 million electron volt. Gain in binding energy for nucleon is about 0.9 million electron volt. Hence the total gain in binding energy is 240 times 0.9 or 216 million electron volt. The disintegration energy in fission events first appears as the kinetic energy of the fragments and neutrons. Eventually it is transferred to the surrounding matter, appearing as heat. The source of energy in nuclear reactors, which produce electricity, is nuclear fission. The enormous energy released in an atom bomb comes from uncontrolled nuclear fission. Nuclear fusion, energy generation in stars. When 2 light nuclei fuse to form a larger nucleus, energy is released, since the larger nucleus is more tightly bound, as seen from the binding energy curve in figure 13.1. Some examples of such energy-liberating nuclear fusion reactions are given below. In the first reaction, 2 protons combine to form a deuteron and a positron with a release of 0.42 million electron volt energy. 2 deuterons combine to form the light isotope of helium. In reaction 13.13c, 2 deuterons combine to form a triton and a proton. For fusion to take place, the 2 nuclei must come close enough so that attractive short-range nuclear force is able to affect them. However, since they are both positively charged particles, they experience Coulomb repulsion. They, therefore, must have enough energy to overcome this Coulomb barrier. The height of the barrier depends on the charges and radii of the 2 interacting nuclei. It can be shown, for example, that the barrier height for 2 protons is approximately 400 kV, and is higher for nuclei with higher charges. We can estimate the temperature at which 2 protons in a proton gas would, averagely, have enough energy to overcome the Coulomb barrier. 3 by 2, kT equals K asymptotically equal 400 kV, which gives T approximately 3 times 10 power 9 K when fusion is achieved by raising the temperature of the system so that particles have enough kinetic energy to overcome the Coulomb repulsive behavior. It is called thermonuclear fusion. Thermonuclear fusion is the source of energy output in the interior of stars. The interior of the Sun has a temperature of 1.5 times 10 power 7 K, which is considerably less than the estimated temperature required for fusion of particles of average energy. Clearly, fusion in the Sun involves protons whose energies are much above the average energy. The fusion reaction in the Sun is a multi-step process in which the hydrogen is burned into helium. Thus, the fuel in the Sun is the hydrogen in its core. The proton-proton (p) cycle by which this occurs is represented by the following sets of reactions. For the 4th reaction to occur, the first 3 reactions must occur twice, in which case 2 light helium nuclei unite to form ordinary helium nucleus. If we consider the combination, the net effect is given by the equation 13.15. Thus, 4 hydrogen atoms combine to form an helium atom with a release of 26.7 million electron volt of energy. Helium is not the only element that can be synthesized in the interior of a star. As the hydrogen in the core gets depleted and becomes helium, the core starts to cool. The star begins to collapse under its own gravity, which increases the temperature of the core. If this temperature increases to about 10 power 8 K, fusion takes place again, this time of helium nuclei into carbon. This kind of process can generate through fusion higher and higher mass number elements. But elements more massive than those near the peak of the binding energy curve in figure 13.1 cannot be so produced. The age of the Sun is about 5 times 10 power 9 years, and it is estimated that there is enough hydrogen in the Sun to keep it going for another 5 billion years. After that, the hydrogen burning will stop and the Sun will begin to cool and will start to collapse under gravity, which will raise the core temperature. The outer envelope of the Sun will expand, turning it into the so-called red giant. Controlled thermonuclear fusion. The natural thermonuclear fusion process in a star is replicated in a thermonuclear fusion device. In controlled fusion reactors, the aim is to generate steady power by heating the nuclear fuel to a temperature in the range of 10 power 8 K. At these temperatures, the fuel is a mixture of positive ions and electrons, plasma. The challenge is to confine this plasma, since no container can stand such a high temperature. Several countries around the world, including India, are developing techniques in this connection. If successful, fusion reactors will hopefully supply almost unlimited power to humanity.
To be tested. Due to its destructive capacity of 11 megatons, the explosion of the bomb was overwhelming and resulted in a large red light illuminating the entire sky. The test was considered to be a great success and led to further tests in the area, including the largest nuclear bomb ever detonated by the United States.
You need to watch this if you struggle with nuclear fission. We'll break it down into 3 simple steps. Step 1. The atom. Think of a heavy atom like uranium, a cluster of pieces held together, the glue called the nucleus. Step 2. The trigger. A neutron smacks into the nucleus. It becomes unstable. Step 3. Split and cascade. The nucleus splits. It releases energy. It releases more neutrons. It makes a few smaller atoms, like dominoes hitting more dominoes. Those extra neutrons hit other atoms, a chain reaction starts. Controlled chain reactions, power reactors, uncontrolled ones are bad news. The energy released comes from mass converted to energy, Einstein's EMC2 tiny mass, huge energy. Quick recap. Heavy atom neutron strike split chain reaction. That's nuclear fission in a minute, powerful, precise, not a DIY project.